All right, we're moving on today.
Pennies are the little thing. What do you got? Quarters or bad? It's silver, it's bad. Say it's silver. But a golden dollar.
4.4, fundamental theorem of calculus, abbreviated as FTC. Fundamental theorem of calculus, abbreviated FTC. We're going to pull together integrals and areas now.
Oh, yes.
So first of all, we talked about. I honestly believe that you're not going to think these are horrible. I mean it this time too. First of all, just a quick refresher on an indefinite integral. Remember we talked, I don't know, a couple weeks ago now, about x plus 2 dx? And I didn't give you a lower and an upper limit. I just gave you this and I said find the integral.
Yeah.
Which really meant that I was giving you the derivative and you had to find the original function. Do you remember that? And we started off the activity and I gave everyone a little slip of paper and you had to find your partner. Remember that?
Yes.
And then we talked about some of the tricks that you could do to figure out your answer after you guys had figured out who matched who. What did you have to do?
Add one.
Yeah, you had to add a power to the x, making it x squared, and then you had to divide by your new powers. You had to divide by 2. And then 2, you know, we could get into all the details again about why it ends up being 2x, but if the derivative is 2, what did you start with?
2x.
I think that one's okay. And then we had to add a little plus c on the end there too. All right, so then just really quickly another one, and you guys may, yeah.
Was there ever like a formula for that?
We did not put it in fancy words. No, we did not. Nope. Secant squared of x dx is equal to. All right, this is the derivative. So what did we start with? Anybody remember?
Tangent C.
Just give me 1 second. I think it's just tan. If you start with tan, what's the derivative of tan? Secant squared. So the integral of secant squared is the tan of x plus c. What did you just say?
Where did we do that or no?
When in our notes, that would have been chapter 2. And section, my guess would be section 2.2 or 2.3, somewhere in there. Okay. But you know what? I am going to give you a cheat sheet for this at some point anyway, so don't worry about that, okay? All right, here we go. What if I ask you to do x dx? And I give you limits. The limits are 1 and 4. What have you done with that up until today? You're gonna start doing it a little bit differently, but what did you do?
Graph a line at 4.
No, graph a line from 1 to 4.
You had to graph this line, and the reason you're doing that is because I gave you a lower and an upper limit. So up until now, you guys would have to graph this like this. You only want the area from 1 to 4. Here's your 1, 2, 3, 4. You did this and you made a shape. What shape is it? You ended up with a trapezoid. So then you had to figure out, what is the length of the base and what is the other base, what's the height divided by 2. So a trapezoid has an area of base 1 plus base 2 added together, multiplied by h divided by 2. So we talked about the bases the bases having, being the parallel sides. So the vertical side. So in this case, we have one of the bases has a, what is this height? How long is this? How would you call it? It's 4. And then this little side over here on the left had a height of
1.
1, and then the height of it, I shouldn't have called this a height. This is a base. Base 1, base 2. What is the height? 3. Has a height of 3. So the area of this thing ended up being 1 plus 4 times 3 divided by 2.
Miss Morgan,
Yes.
that's not a triangle? No, because it starts at 1.
You know what? That's interesting that you say that because in a minute we're going to talk about this being a triangle. But no, it's not a triangle. Do you see this right here? That like cuts the tip of the triangle off. Okay? So we have 1 plus 4 is 5 times 3 is 15 divided by 2 is, you end up with an area of 7.5. That is what you have done until now. But now what I would like you to do is think about this in terms of an integral. Integrate this for me. What is the integral of x? Yeah, so from 1 to 4, x dx, that is equal to, remember you add a power on, makes it a 2, and then you have to divide by 2. So this is equal to 1/2 x squared. This formula, though right now it does not look like that, this formula, this equation you came up with, 1/2 x squared, is actually the formula for the area of this in terms of a triangle, which is what Larissa just pointed out. Isn't that a triangle? Do you see the triangle right here?
Yes.
Well, regardless of how big or how small this is, if we called the bottom of the triangle x, what is the height of the triangle? It's going to be exactly the same thing. When I say the bottom, I mean the entire thing, not just from 1 to 4. I mean the whole thing would be x, and the height of it would be exactly the same. So the area of this triangle would be x, base times height, x times x, divided by 2. Well, what is x times x?
X squared.
X squared. So we have x squared divided by 2. Are you with me here? Yeah.
No.
Okay, hold on. Yeah.
Are they both the same because the equation is just x dx? Like, is that why the height and base are the same thing?
No, it is the same because on this line, every x value matches its y value. So any point along this line has an x value and a y value that's exactly the same. This is the line y equals x. So if I picked this point right here, it might be the point 2, 2. It might be the point 4, 4. Regardless, if I look at the triangle that's created, any triangle that I make underneath that line has a base and a height that is exactly the same. So if I call the bottom x, the side of it is also x. Does that make sense?
Yes.
Yes, Mary?
Okay, so you know how you said every x has a value of the same? Like, what if, like, the graph was cut?
What if the graph was,
Like, that did not exist. It have a graph. There's no graph in this graph.
not at least to begin with. So let me try, here's your line, y equals x. So if I drew this triangle right here, this point right here might be the point 5, might be the point 5, 5. So how far over is that point? It is 5 over. How far up is that point?
5.
It's the same thing, it's 5. How would you find the area of this triangle? Well, you would take the base, 5, times the height, which is 5, and you would divide it by 2. So you go 5 times 5 divided by 2. Can you agree with that?
Yes.
That's if the point is 5, 5. What if it's not 5, 5, it's just anything? say x. Well, if this is x, what's this side over here?
Thanks.
It's the x. So when you find the area of this triangle, you're going to go x times x, which is x squared, and then you're going to divide it in half. Because that's the formula for finding the area of a triangle. The base of it x times the height of it x divided by 2. So the area of this triangle is a half of x squared, which I know is not how you are used to looking at a triangle. And this happens to be the area of a triangle when the base and the height are the same. But usually they're not the same. But for this case, it is. China.
So on the left side, where you wrote 1/2 x squared, you wrote that because I get why you wrote it, but it's the same line.
1/2 x squared.
Yeah,
Is the same-
It's a line. Is it like
I took the integral of x.
yeah?
The integral of x is x squared over 2, which is the same thing as a half of an x squared. X squared divided by 2?
Yeah, I get that it's a 1/2 x squared.
Okay.
I'm saying like is that graph is the same thing as a 1/2 x squared.
Yeah, yes.
Isn't x squared like a curve or no? That's what I was confused.
Okay. So you're looking at this going, isn't that a parabola?
Yeah.
This, okay, yes, it is. This is what I graphed over here though. I graphed x. I didn't graph this. And it just so happens that if I look at this kind of in an obscure way, it ends up being
Part of the parabola.
part of the parabola.
Okay, that's
Yes.
what I'm thinking.
Okay, yeah. You can't think of this as what I graphed over here. I have taken this line and I'm going to try to find the area underneath it, and it just so happens that the area underneath is going to end up being a quadratic situation, which
So
is
it's like
not.
basically a zoomed in section of the parabola.
No, it's not that. It's not that.
Then it's just never mind.
It's just
skip it.
x.
Skip it.
That's the formula.
This is the formula
Yeah,
that
I
you are
get it.
going to use to find the area. It just happens to be a quadratic. You cannot think of this as a graph. Don't think of this as a graph. It is the formula that you're going to use to find the area under a curve.
Okay.
Yes.
Okay, I'm still confused. So the x squared over 2 is the formula?
Yes.
Okay,
Or a half x squared is the formula.
okay, so it's one of those.
Yeah. Either one of these. These are the same thing.
And we did that to find what?
Area.
To find the area
Of a triangle.
of this triangle.
And it
Of
has to have like
of
the same.
a right triangle that has a base and a height that are exactly the same.
I got you already did 7.5.
Oh my gosh.
She's showing you another way instead
Wow,
of
this
using
is not going the direction that I thought it was going to go. I am right now. Let me explain what I am trying to do. You guys, in the last couple of days, you have created these weird shapes underneath curves. You've created trapezoids. You've created circles. You've created rectangles. But what I'm trying to get at right now is that you are not always going to get nice, pretty pictures like trapezoids and triangles and rectangle stuff. You're going to get really weird things. Like, for example, what if I ask you guys to do this? If I give you some weird shaped graph that looks like this, in fact, Gutnaz just gave me a picture the other day that was very, very strange, and she said, help me find the area of it. And so the process that I'm going to show you today allowed me to help her find the area of it. So what if I give you this picture and I say find the area underneath it? So in other words, I want you to find the area from here. I want you to find the area within this squiggly mark. What I'm going to do today is show you how you can do that. That's what I'm trying to get at. So yes, you told me just a few minutes ago, don't we already know what it is? What did we come up with for our area to begin with?
7.5.
7.5. We already knew it was 7.5. But what if it's weird like this and you can't make a trapezoid out of it? Or you can't make a triangle out of it? Then you're going to have to explore some other options. That's what I'm trying to show you today. Hang on, please, you guys. Please, 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 hang on. Don't give up yet. It's not bad. I promise. grab it, that would be good. In fact, I actually wondered, I was thinking maybe I could scan that in and show them too, but he should show me a picture that looks like this. There was a parabola, and then it had a line right here, and the question was, what is the area of this region right here?
Would you just find the area of the triangle?
Well,
Subtract
this right here is a triangle, right? Would you agree? So that's not bad. You can find the area of that very, very quickly because there were dimensions and stuff, and it was a straight up and down height, so it was very, very easy to find that. But what about this? This is weird. It's got this hoop here. So what are you going to do to find the area here? And that's what I'm going to show you is this process that you can use to find. I think I'm good actually because this is pretty much what the picture looked like, wasn't
It's
it?
different a little bit.
Different a little bit, huh? That's all right. This is good. I think this is good enough. So this little region right here is the part that we don't have a formula. What is it? What is it the shape of? It's not a triangle. It's not a rectangle. It's a weird shape.
a regular volume.
So what I'm going to do is show you what you can do to find the area of weird situations like that. So, getting back to this, I'm nervous to get back to this now. I graphed this line. I graphed X. This is what you guys have been doing. You graph the line X. I want you to find the area underneath this, this line, but I want you to find it from 1 to 4. And we talked about how this is actually a trapezoid, and we calculated that if we were to use the trapezoid formula, we would end up with an area of 7.5. Everyone in here, pick your heads up right now. If your head is down, pick it up and listen to me right now. This is unbelievable. If you don't want to be in here, then you can leave. So you have this triangle that is actually, this trapezoid is part of the triangle. I talked about the bottom of it having a base of x and a height of x. Because it's underneath this line, y equals x. So any point, anywhere that you draw a triangle on this thing, the base of it and the height of it are going to be exactly the same. X times x divided by 2. So the area of this, and I know we're not talking about a triangle, we are talking about a trapezoid, but I'm getting somewhere with this. Here's the triangle. X times x is going to get me the x squared divided by 2. So we have this formula here, 1/2 x squared. This is the integral of x, 1/2 x squared. So if I find the area of the big triangle, so in other words, if I start here at this top part right here, I go down to the corner and then back over here and I find the area all the way up to 4, how do you calculate the area? In other words, it has a bottom length of 4, it has a height of 4.
1/2 times height.
You're going to take 1/2 times 4 times 4. What is 1/2 times 4 times 4?
4.
8.
Oh.
4 times 4 is 16. Divided by 2 is 8? Yes?
Yes.
Okay, but remember, we are not finding the area of this entire shape, are we? We are finding the area of only, and I know this picture is getting very, very messy now, but we are only finding the area of this trapezoid. So what we need to do is get rid of this little triangle right here in the corner. Does that make sense?
Yes.
We have the whole area is 8. We need to get rid of this little corner right here. How do you find the area of that little triangle in the corner?
Subtract 7.5.
1.
What's the base of this little triangle? 1. So we're going to take half of 1. What's the height of that little triangle? 1. So we take a half of 1 times 1. What's half of 1 times 1? It's a half. So now if I take the whole triangle's area, this whole thing, and I take away this little teeny tiny corner right here, I'm left with the trapezoid. Yes?
Yes.
Yes.
So if I take the 8 and I subtract 0.5, what is 8 minus 0.5?
7.5.
And isn't that what we said it should be?
Yes.
So my point is this. You don't need to draw these pictures anymore. You can just find the integral of whatever the function is, and let me show you what you did. You took this 4 and you plugged it into this x value right here, and then you took the 1 and you plugged it in for that x value right there, and you subtracted them.
Oh my gosh.
That's what I'm trying to get at. But listen, I want to say this. Had I just said this, there would have been 5 people with their hands in the air saying, why? Why does that work? Why does that work? So I wanted to try to explain to you where this is coming from and why it works.
Okay, so
I kind of want to cry.
I want to cry right now too.
So all of it, can we make a new video? 'Cause I feel like whoever's watching this.
There's only going to be a couple people that watch it, and they'll be fine with it. And you don't need to worry about that. I need to worry about that.
Okay, so it's only
Okay.
4 plus 1. Okay, never mind. I'll just.
So I'm gonna put this in nice words for you here in a minute. I was trying a little history. This is why it works. Here we go. This is what you need to. Okay, the fundamental theorem of calculus says this. I'm gonna abbreviate FTC. Says this: if you have an integral with a lower limit and an upper limit, and some function, you need to take the value of the integral at the upper limit, and this is how you note it. You do this, f of a. And so you might want to make a note that that big F right there stands for the integral. So in other words, you take this, and I didn't mean to write A. I apologize. It's supposed to be a B. My bad. You take the value of the integral at the upper limit, and you subtract from it the value of the integral at the lower limit. That will get you your area.
Yay.
So this is the area. So let's try one. So some of the ones that I give you are going to be things that you could do. You could draw a picture for. You could draw a picture. You could calculate the area. But at some point, they're going to end up being weird and curvy. And there's going to be no formula that works. No easy formula like circle or triangle or square or rectangle. So let's do this one. Can I flip pages, you guys?
Yes.
Let's do the integral from 0 to 2 of 2x squared minus 3x plus 2 dx. You could graph it. And then try to calculate the area underneath. But if you graph that, you will notice that it's curvy, and I don't know how you would do it. So we're going to use our fundamental theorem of calculus theorem to do that for us. The first thing you have to do is find the integral. So what is the integral of 2x squared? It's going to be 2x, what do I do?
Cube divided by 3.
Very good. 2x cubed divided by 3 minus 3x, what?
Squared
Divided by 2
plus 2x.
plus 2x. Now, a new thing, a new
Plus
notation.
C.
Okay, now plus c. I want to explain to you why when you do these you don't have to use a plus c, but give me a minute first and I'll talk to you about that. A new notation, if you put a vertical line like this right at the end of your integral, that tells you that, not that there's nothing else, it means to you, it's kind of like your reminder that this is the integral. Okay, this is what you want to do. So find the integral, do this, put a 0 and a 2 on the top and the bottom of it. that will tell you that you have already found the integral. Because some people will get confused and think, is this my original function or is it my integral, okay? This is the notation that mathematicians use to denote this is the integral. All right, so now what we need to do according to that fundamental theorem of calculus, you take the integral, remember the capital letter F meant the integral, f of b minus f of a is equal to. So we need to take this up here, this 2 up here is the b. So we need to take that 2 and we need to plug it in for our x's in our integral. And then what we're going to do is find f of a. So we're going to take this 0, which is our a, we're going to plug it in for our integrals and we're going to get an answer there. And then we're going to subtract them, and that will be the area underneath this curve. So, one suggestion you might want to take, go to y equals, type your integral in, that will make it a little bit easier for you to figure out what is the value of the integral at 2 and what is the value of the integral at 0. So, f of b, in this case really means f of 2. So you take that 2, you plug it in for your x's, and get an answer. Anybody have it yet? If I've done my calculations right, it ends up being a fraction. 10/3, I think. Probably shows up in your table as 3.3 repeating. So you end up with 10/3. All right, and then you need to do f of a, which means f of 0, which is 0, I think. Yeah, so if I put in 0 for all these x's, you get 0. So then if you do f of b minus f of a, that means 10/3 minus that's it. So let's, I'm going to try one more example, and oh, let me talk to you about the plus c's. Technically, when you find an integral, you're supposed to have that plus c at the end. So you don't need to include the plus c's, but I'm going to put the plus c in here just for conversation's sake for here for a minute. If I put a plus c in here, and then I add it down here, and I calculate the value of that integral at 2, this part right here is going to have a 10/3 plus c. Would you agree? And then this part would have a 0 plus c. But then we subtract them. So when you subtract this plus c and this plus c, when you subtract them, what's going to happen to your c's? They're going to cancel right out. So no need, Christina, put the phone away. There's no need to have the plus c's there anymore, okay? All right, one more example. Let's do the integral. One with the square root. I'm going to do one with the trig function. 0 to pi over 4 of secant squared of x dx. Now, secant squared graphs, crazy, curvy, all over the place, find the area of it, good luck. So that's why we use the integral. So help me find the integral first of all. What is the integral of secant squared?
Tan x.
Tan x. No need to put the plus c, but remember if you do this, that kind of tells yourself, okay, I've already found the integral. So you go from 0 to pi over 4. Find f of b. F of b in this case means you are calculating f at what? Pi over 4. So what is the value of tangent at pi over 4? So make sure you're in radian mode, and you can just type in tan of pi over 4. Or you can go to your trig tables, your orange trig tables, and go to pi over 4, look at the tangent row, you should end up with 1. So you get 1. F of a is the same thing as f of 0. What is the tangent value at 0? I think it's 0. Now, it's ironic that both of the examples that I have given you have been 0 for the second value. That's not always going to happen. In fact, it usually doesn't, so I apologize if that happened like that. So now when you do f of b minus f of a, you have 1 minus 0, which is